For our last speaker, for our longer talk, we are going to be having Jessie Kendall-Bar talking about how biosensors and 3D modeling are being used to track and integrate sleep and movement data. And I am super, super excited about this talk. I got a sneak peek of the presentation beforehand, and I was totally floored. So I'm going to hand it over to Jessie to walk us through that now.
Great. Thanks, Alex, for that introduction. And thanks for being here, for tuning in. I just submitted my survey in the ad break, so I'm very proud of accomplishing that. Yeah, so this is going to be a little bit different because I'm coming from more of the side of an academic, and I'm trying to tell you what I've done in my dissertation and then what I want to do in the next steps of my career, and where I would really appreciate some help from people like you that are designing new technologies and new softwares and new data packages so that we can really learn important things about animals. Specifically, their physiology and behavior is what really interests me. So as I said, I'll talk briefly about the problems that I ran into during my dissertation, and then that feeds in directly to my plans for future research as I start to create a lab. So during my dissertation, I combined engineering, data science, visualization, and a bit of machine learning to look at the sleep patterns of northern elephant seals from the individual to the population level. And I think in this community, we're all on the same page as biologging scientists who are asking animals to carry our instruments into the field. We need to minimize the impact of those tags on the animals and also maximize the impact of every one of our data sets. So I worked with my intern, Ritika Mukherjee, on this literature review, and we found that the vast majority of work to detect sleep in animals has been done in captivity and with invasive methods. So our study tries to bring the study of sleep into the wild with non-invasive methods. And to design this surface-mounted sleep recording device that measures EEG, or electroencephalogram, alongside ECG, the hardest part is to make sure that each of the sensors is electrically isolated from one another. So I designed a head cap and a system for the wires to remain electrically isolated and pressure-proofed up to 2,000 meters deep, where the elephant seals could dive. And we came across some interesting, I can talk maybe for days about the different sources of noise that we came across. And it wasn't the capacitors, but lots of other technology that we need to deploy on these animals to find the tags again, like VHF transmitters or anything with a battery and anything with a voice, whether that's electrical or sound. And then the other source of noise is actually coming from the animal itself. So the large heart of an elephant seal is actually kind of a problem when you're trying to listen to the smaller signals that are coming from the brain. So we used independent components analysis to try to disentangle what noise was coming from the signals from the heart and what noise, what was the signal that we were looking for, the signals from the brain. So we had some success in just disentangling those two. And then we had a new challenge of how to score sleep for an animal that we have never recorded sleep in the wild for. So we had to come up with a criteria for what is slow wave sleep, what is REM sleep, what is waking. And then we even came up with a new state called drowsiness, where they're sort of going in and out of slow wave sleep at a frequency of about 10 seconds. We had to talk to experts all over the world to try to establish new criteria for categorizing sleep. And then adding physiology to the field of movement ecology presents a whole nother challenge, where we're adding essentially 18 dimensions of complexity to the data analysis challenges of movement ecologists that are thinking about animal movement in 3D, in space and time. So when we're looking at this much data, it's hard enough to make space on the screen. I'm only showing about half the signals that are recorded on this neurologger. And many of these signals are actually trying to paint a three-dimensional image. So traditional tools for analyzing this neurophysiological data that show us spectrograms alongside time series data are not usually made for measuring sleep across space and time. So I had to build my own end-to-end visual analysis pipeline to see the patterns in 3D movement alongside the animal's internal physiology and brain activity. So I talked about how we deal with the physiological data. We categorize it into these discrete categories of sleep state and respiration state. And then we have to analyze the motion and environmental sensors. So we can use some math magic to transform the raw signals of the accelerometer, gyroscope, and magnetometer into pitch, roll, and heading. And we can get an estimate of speed and use that to create a three-dimensional track using dead reckoning. And then we can paint on the labels of physiology on top of that three-dimensional image, showing us a representation of physiology across space and time. But that's not enough for me. I really wanted to see and experience the behavior and physiology firsthand. So I built this animation pipeline that uses Autodesk Maya, which is a software that is used in the movie industry. And I paired the sound to the heart rate data to get an output that really recreates a scene from the open ocean. I didn't share my sound, but you can hear the heartbeat of the elephant seal, and then it starts to go down as the animal leaves the surface. So I'm not going to make you sit through the entire 30 minutes of this deep dive for this northern elephant seal, but visualizing dives at this fine of a time scale can lead us to some really exciting new hypotheses about how these animals control their heart rate and their perfusion while they dive. In the case of this sleep study, it allowed me to interpret the seal's internal neurological patterns alongside its 3D trajectory. So this is hypoactive Heidi. I gave her a cute name so I could remember who she was. And she leaves the surface, she swims down about 100 meters, and then as she reaches about 150 meters, the slow waves start to emerge in her brain. So you can see those in the spectrogram at the top of the screen. And then there's a flip in her body posture where she turns upside down, and that enables the transition to REM sleep, where presumably she has become paralyzed about 200 meters below the ocean's surface. And she continues falling like a leaf for another 150 meters. And then at around 263 meters, she'll decide to wake up and swim back to the surface. So these visualizations are really helpful from an analytical perspective. They allow us to see that her neurological state is actually tied to her three-dimensional behavior and 3D movement, but they're also helpful to communicate our findings. So we use these animations alongside our paper as supplemental material, and our animation was actually featured by the New York Times and the Atlantic and contributed to the paper's reach in our community. And then we can use that biomechanical signature of sleep to build a detector that, that operates on simpler data. So in this case, we only have depth and time, but we're able to use that signature to estimate the amount of time that these animals are sleeping. And the great part about this is we now have access to a much larger data set. With over 300 animals, we can get a daily time estimate as they travel across the Pacific. And that leads us to an estimation of a very low sleep quota for time at sea, only 2 hours a day for up to 295 days that they spend at sea. And that's going down from the amount that they sleep on land, which is about 10 hours per day. So that degree of flexibility between 10 and 2 is unparalleled among all mammals, and raises this really important question of what is the baseline sleep requirement for an animal that oscillates between 10 and 2. So I think that it's really important to help answer some of these questions so that we can turn our focus towards conservation and inform the management of protected areas and how that's going to trickle down into the sleep and health of these animals. So overall, my dissertation used a really small subsample of high-resolution electrophysiological data to identify a proxy for sleep that we can apply over a much larger data set. And I think that generally, although we're making huge strides in making these devices smaller, we need to do more to continue to minimize animal impact by making those physiologgers that record sleep smaller. But we also need the cyber infrastructure to help us translate what we find with those high-resolution loggers into the sort of species level patterns that we see, as well as across species and across fields. So that's really what is informing my research vision for the future, where I want to continue to build new tools for fundamental ecophysiology ecophysiology research. So that's heart rate and brain activity in new species. Build new tools for visual analysis that'll help us speed up our interpretation of that data. And then build those analytical tools into comparative systems where we can start bringing in the sleep patterns of an elephant seal and compare those to maybe a species that is of high conservation concern. And then visualizing those insights is something that I'm really excited about, and I think that that can build momentum for conservation as a whole. So for bioengineering, I feel like, even just the expertise that has just been shared, and by Phil, these secrets about, what is it, the capacitor that's creating the ultrasonic noise, or is it something else? There was something that I heard that super glue becomes conductive when it cures. Like, these are the secrets that we need to be sharing with each other so that we don't run into these problems after it's been deployed on an animal. So yeah, we really need to find forums to share these expertise, these little nuggets of wisdom. So I've been developing some new tags during my postdoc. So basically translating the device for elephant seals to look at epilepsy in sea lions, to look at brain activity in freedivers, and then to improve the design for heart rate detection in baleen and toothed whales. But one thing that I've approached WildLabs about that I'm excited for is the ability to lead a workshop where we bring these experts that have these nuggets of wisdom inside a room and really just document it. And that's our only purpose, is just to write down all the weird things that happen when you mix two compounds together, or when you put two loggers orthogonally to each other or parallel. We just get it down on paper first, and then we think about how to make courses for graduate students, undergraduate students, and sort of the next generation of the people who are going to build these physiologging devices or these advanced loggers that are smaller than ever. And then as a postdoc, I've also been part of this AI and Science postdoc fellowship, which has been mind-blowing in a lot of ways, but mostly because I realized I didn't know anything about coding. And through this program, I've learned a lot about coding in Python and how to begin to leverage AI. So for my dissertation, I manually scored 5.6 million seconds of data to the nearest second, which was thousands and thousands, probably millions of actual manual annotations of when these animals were transitioning between sleep states and respiration states and out of water, into water, etc. But that's really important. That manual process is really important. I mean, Lars was talking about the importance of a really good training data set. So it's not that time is wasted, but now how do we leverage that? So we've encountered this completely new species in a new context, and we've created a method for sleep detection. How can we use that to make an automated method to speed this up in the future? But this is going to cause some serious computational hurdles where the data itself is over 10 gigabytes. So the generated features from this kind of data set will easily reach 100 gigabytes, and they have to be stored in memory while you're doing the processing to train and evaluate a model. So that's where supercomputers come in handy. So I worked with 5 master's students who are here at UC San Diego that were engineering features for a flexible sleep scoring model that would be able to run on our data using the cloud resources in Nautilus, which is this free institutionally run cluster that we have access to, that anyone has access to. And so they named this custom tool Marine Somniac, and it's built in Python, uses Streamlit. So it's a bit more simple than maybe an app that uses C or C++. So our hope is to make this an accessible research tool where you can visualize the automated sleep scoring data alongside the features, and you could switch these categorical labels out to be any sort of behavior state that is categorical. So we used a light GBM gradient boosted decision tree because that allowed us to rank our features and have a little bit more interpretability. And then we've been developing this tool alongside several other tools for AI and ecology. And I led this workshop earlier this year in March, where there were 5 different projects using AI for different challenges in ecology. And I think that this is where I see Wild Labs' potential to sort of facilitate this kind of innovation, this kind of bringing of people together. So we were able to get everybody together in a room for 3 days and create a bunch of useful software and think about how we can really leverage computation and AI in ecology. But mostly, again, I told you I knew very little about Python coming into this postdoc program. And since then, I've learned all of these fancy jargon things that have helped me become a better programmer. And I think that even though it can be frustrating for me to learn how little I know about Python, this type of training is really what's missing from the training of movement ecologists and what could really launch us forward. So I think that one thing that we're missing as a field is not only this computational training in AI, but also a shared data structure. And that can really help accelerate the innovations that we're making. So I've been making these Python tools for biologging data. And I don't know if any of you have tried to synchronize data to video, but there's no good tools, I think, that use open source software to do this. So we've been working on this Python tool that allows you to visualize time series data alongside the 3D model and video data that's associated with that recording. And it uses web-based framework using Dash and to display React components that are synchronized so that we can actually look at our data alongside the video. So this is an animal, a penguin in Antarctica that's swimming under the sea ice and comes up to grab some fish. You'll see it grab the fish. So this allows us to not only see the video paired with the data, which I think a couple of software tools allow you to export a video like this, but this is an interactive environment where you can decide to zoom in or decide to rotate the model to see it in higher resolution. And then I thought it was fun. This penguin found some Weddell seals fighting with each other over access to the breathing hole. So yeah, and then the app building, I've been also dabbling in making a mobile-friendly data entry app because entering metadata is one of the most painful things we do. And then I've created some documentation and tutorials. So we've created this structured DiveDB to house this type of data where you're using multiple loggers on the same animal that have multiple sensors that need to be synchronized and visualized together. And ideally, that would allow us to more efficiently label the data with these new tools. And then this is just an example, but we were able to get a pretty large data set into this database, about 300 gigabytes. And then that helps us query diving data much more quickly. So we can just select one out of these 655 animals and see the data from it. So our goal is to build this out for multiple data types and multiple species, but we need Wild Labs' help to do that. And we're really excited to work with people like this. And this will also help us visualize the data in this new Explorer that we've created. So you can go to our prototype now to check it out, but this is a way to show physiology alongside 3D movement and behavior really flexibly for different species, and just share your data with others in this format as well. So yeah, I think that's all we have time for. So I'll stop there.
Thank you so much. I think I speak for many or most people on this call and say that this is all so cool in a way that I've like never seen before. Like the chat is just blowing up with people being like, this is awesome. There are some questions for you in the chat. I want to be selfish and ask one first. Um, what do you want people to come and talk to you about? Like if you get an email in your inbox asking about your work or asking to collaborate, like what is your dream scenario for what somebody comes to you asking for or wanting to collaborate on?
Okay. Any of these four things, basically. If you want to build tags, contact me. If you want to build Python tools that leverage AI, contact me. If you want to help us do the really boring task of like, okay, this lab is using this MATLAB data format. Like, how do we map all of their metadata fields onto our metadata fields in our netcdf format? And you just build a little data input script, and then like that will unleash so much beauty and allow us to visualize all of that lab's data. So that kind of task would be really helpful. But if, it all depends on the skill level of people coming to me. If you're interested in biosensors, that's what I would love help on. We're using Python, Dash, React, Docker, so like expertise in any of those, and maybe some people who know MATLAB too, so that they can help translate between the languages, would be great.
Awesome. And it looks like we had a question in the chat from Anne. Anne, do you have access to a microphone to ask your question? If not, we can ask it on your behalf.
I think I do. Can you hear me?
Yes, we can.
Okay, great. No, so Jessica, I work with an organization that does a lot of government contracts with the United States regulatory body in like the marine sector. So what they're always looking at is what kind of studies can we run and what kind of data that we can collect that will then tell us how we can regulate industry to reduce impacts to wildlife. And so I'm wondering, so a lot of what they do is, okay, let's tag animals, let's see where they go, let's see what their behavior is. And then do any of these certain behaviors mean they might be more at risk to certain industry activities or ship strikes or this sort of thing. And I'm wondering how you think this information applies, because what is new about this is the cognitive neurological processes that are going on in conjunction with the physiological behaviors. And I wonder if you think it has any application for understanding if an animal may be more at risk because of their, not only what they're doing physically, but their neurological state.
Totally. So yeah, I think we're still quite a ways away from being able to read the mind of an animal using EEG. That stands for humans and for animals. But we do have a lot of insights that physiology gives us that are even more simple to interpret. So for example, in this disturbance dive, this elephant seal probably hears something, although it can't be certain because we didn't have a hydrophone. But there's some behavioral change right here where the animal decides to extend its dive for about 10 minutes before it goes back to the surface. And that coincides with a drop in heart rate to 3 beats per minute. So if we can find these little instances where you could probably get that from the behavioral data alone, but then you get confirmation from the physiology to see that there's really an impact to the animal and maybe a decision switch that happens. So I think that building out these browsers to visualize the perceived sound at that animal's location, as well as potential sources of sound in the environment, it could be a really useful tool for what you're talking about, because if I zoom out a little bit, there's a hydrophone that just sits on this slope over here called Mars that's run by Mbari. And that data is right on this slope, actually, that's run by Mbari, and that has access continuously to sound detections in its environment. And if we're able to model the sound that animal experienced, both using AIS ship data and that type of hydrophone data, we can really learn more about how to manage their habitats and protect their sleep, which I think is another interesting tool that these types of sensors will give us.
Yeah, that was one thing I was interested in, is are they more vulnerable if they're, say, asleep or awake, or can you monitor that or understand that maybe they sleep less if they're in an environment, say, where there's just a lot of noise due to industry or something like that. Anyway, they would absolutely love this. And they would also love the visualization from a communicating with the public standpoint. So I may contact you. I'll probably contact you later.
Yeah. So just one quick follow-up to that. This sleeping dive right here has a bunch of REM sleep, and then this is the disturbance dive where the heart rate went down to 3 beats per minute. And then the very next dive, the animal decides that it's safe enough maybe to go back to sleep, to have a bunch of REM sleep, to turn upside down, be paralyzed for 10 minutes and wake up. So that might tell you a little bit about maybe what it determined the disturbance, whether that was determined to be a risk or not. But I think that, this tool can help us understand the impact of physiology on behavior.
Thank you so much for that question, Anne, and for that answer, Jessie. We've got some more questions in the chat, but I'm going to direct you there to answer those questions about sensors. And we're just at time now. So I want to thank you all both for coming to Variety Hour and for our speakers for those awesome presentations from Lars, Seamus, Phil, and Jessie. I'm going to end the recording in just a few moments, but you're all invited to stick around for after hours to have a more casual conversation about the talks that we heard today and also anything else. So thank you again for coming. Happy Halloween, and we will see you next month. Bye.